First thing, I will go to File. File, New Model. I don't know why it's heavy today. And I will turn my units to be ton meter because I have my forces are in ton and my dimensions are in meter. And I will go to grids only. So I have how many grids I have in X directions? 3. And how many in Y? I have Z is 2. But Y there is no grids because this is an XZ problem. In direction, I can go with 2.25, which is the spacing. And in Z, I have 3. And then I will say, okay. And then I will convert the XY plane here to XZ so that I can see my XZ. And then I will edit grids data, modify. And I will make this 2.25 plus 4, 6.25. Say okay, right? Okay, so this is a little bit difficult problem because I don't have a specific cross section to define, but it's only given in E and I. E goes in the definition of the material. I goes in the definition of the cross section. Okay, so the first thing is I need to define a material, and let's go with, what was that? Oh, A or I will be in the cross section dimensions. Okay, so modify the material, and the only thing that I need from the material is E, and in my problem is 2100 ton per centimeter square, so 2100, and this is ton per centimeter square. I multiplied by 10 to the power 4, so I add 4 zeros to convert it from ton per centimeter squares to ton per meter square. And then I will say, okay, so this material is right now. Second thing is I want to define a section, a frame section that has an area is equal to 13.2 centimeters squared. So you go to define frame section and add new property. And then we will not choose a steel or concrete. We will go to other materials and you will find general. And when you hit general, it asks you, this will be frame section 1, and you give it the area of this cross section. And since this is a truss, I only care about area, I don't care about the inertia. So it will be 13.2 centimeters square, but I want to make it meter square. So this will be 0.00132 because I have to multiply it by 10 to the power -4 to convert it from centimeter square to meter square. And then I will say, okay. And here's my section. And I need to make sure that it has the right material that I defined with the E that I input, the E that has 2100 ton per centimeter square. And then I will say, okay. So this is the right frame section that has E is equal to 2100 ton per centimeter square and A equal to 2.2 centimeters square. If you didn't do this step, your analysis will be messed up. Okay. Okay, you want to say that the area is 0.45 multiplied by 0.25, but this is not rectangles, this is oval. This is a general area. So we cannot multiply it as a rectangle. But this section, if you want to check the section properties, you will find here, this is the area of your section. And actually, let me tell you, any cross section that you define, you can reduce the area. Like you can tell SAP2000, this is a rectangle cross section that has section of 25 centimeter by 0.7 centimeter, but the effective area, and you can input the effective area of the section, and you put different area, and the SAP2000 will deal with this member with another area. Some people use this option if you are dealing with a cracked concrete, if you are designing a tank or something. This tank is designed as a cracked sections. We assume that the sections are cracked, and we assume that not the whole cross section is effective, and we need to reduce the area. So we input a section and we use an effective cross section. Here, this is my area, and then I say okay, and my name, the section name is F section 1. I will say okay. Right now I can draw my structure using draw frame element, and I make sure that I have the right element here. I have one here, another one here, and another one here. Okay. And I have hinge at all these joints, assign joint, restrain, hinge, and I will say okay. Right? No, there's no fixed in trusses. It's all hinges. Okay. Yep, no problem. Okay, so this is my truss. What is missing right now? What should I do? Loads, right? Okay, I select this joint and then I assign joint loads forces, and let's put the forces as the dead loads. What is the value of the force in Z? -5, in X 2, and I will say apply OK. Oh, assign joint load forces. Okay, this force shouldn't be in Y. This should be 0. X should be 2. So make sure that you have replaced existing loads. So what we'll do, it will replace all the loads and put this new loads. So when I say OK, my forces right now is right. Okay. Okay. So what is still missing? I have to release, right? Why I have to release? I know that the moment is 0 at these hinges, but it is not 0 on the top. It will deal as a frame. So we will see it as a frame until you select these members and say assign frame release M33 at the start and the end. I know that the start is already 0 because it has hinges, but you can make it 0. It doesn't make any difference. So it's the same thing. All right. Okay. So right now I have all my moments. Yeah. You have a question? Okay. So I have all my members are moments released. Do I still missing anything? Okay. How about the on weight? It's included, right? And I don't have any on weight in this problem, right? So I go to define load pattern and make the on weight of the problem 0. And I make sure to say modify and say OK, right? Because if you make this with on weight, it will deal with this it will have a bending moment. And in trusses, we neglect the on weight, okay? Because it's minimal with respect to the external load. Okay, or sometimes we concentrate the weight on the joints, like put it as a concentrated loads. All right, so right now my structure is ready to be solved. So what I'm going to do, I will save it first. And let's say truss number 3. Okay, 3, save. And let's run this problem, and then let's don't run model, run now. Okay, done. Let's see what is the deformation here. Okay, look at this deformation. Okay, we have you guys remember what is Newton we have? It was 3.7 or 0.5 10 to the power -4, which is 0.003.37, which is 0.004. Same thing here. U3, it's a negative 3.34 multiplied by 10 to the power -4. So it's a negative 0.003. Okay, so deformations are right. Let's find the reactions. Hey, sir, can you bring up safety? What was that? It's I think you can, and some in the options maybe. Like the rounding, the options, I believe you can get it. I can search it, but no. Hey, sir, you know how you show they replace existing loads? They replace existing loads, yeah. When I was in the home, right, you doing the sample in the class, and you put the dead load, then you go back to doing live load. Live load. Okay. You did replace existing load you have. No. You can do replace existing load, but dead load is completely different pattern from the live load. All right. Okay, so the next thing is to find the reactions. So let's find the reactions. If I came here, joints, I want to see the reactions from dead. Okay, so let's see the reactions here. I'm not sure. Okay, let's look at the reaction. We have 3.09. Let's look at reaction here. 3.08, almost the same. Right? It's all about rounding. And if we look at the reactions global, 1.65, -2.2. So here, 1.65 to 0.2. Same reaction. Same thing here, 0.2 and 0.27. This is reactions. Let's get the internal forces in the member, like compression or tension. So we will go to frames, and then as there's no moment, we need to the axial force. Let's see what we have here. So this member has 0.333. Somewhere here. 0.333. The second member, this member, has negative 3.08, which is this number, 3.09. The one that we calculate. This is 3.09. And this one is negative 2.75. So let's go here. We'll find 2.75 the compression of this number. Okay, so this is the solution using SAP2000. Can you imagine just the 3 minutes? Actually, you can build this model in 3 minutes. It saves you 1 hour of solving this problem. And actually, you can end up solving it not correctly because you did some math errors. And you can actually develop a MATLAB code that can solve this problem. You'll just need to define the metrics, and you do all the multiplications of matrices so you don't miss anything. And you can build your own MATLAB code that can solve the problem. Okay, all right. So